Hello, and welcome again to World of Orthopedics. This is Cameron Sabet. This is lecture 2 on hypothesis testing and common statistical tests. So last time we built the foundation, understanding data types and study designs, and today we're diving into the deep end, hypothesis testing and statistical tests. So this is where most med students get lost, but I promise you by the end of these minutes, p-values will not scare you anymore. Let me start with a story that happened during my research. We'd spent quite a while collecting data on a new ACL reconstruction technique. Finally got our results. New technique had a 5% failure rate versus 8% for the standard technique. My PI was excited. This is going to change how we do ACLs. Then we ran the statistics. P-value was 0.08. It was not significant. Our faces dropped. 6 months of work, coding and doing a lot of the stuff, and we couldn't really publish a positive study on it. But here's the thing. Was our new technique actually not better, or did we not just have enough patients to prove it? That's what we're going to understand today. So today's lecture is going to be super practical. We'll start by understanding what hypothesis testing actually is, and I'll explain it without using confusing probability theory. Then we'll decode p-values and confidence intervals, because everyone throws these terms around, but most people don't really get them. And after that, I'll show you how to choose the right statistical test. This is huge for research. And finally, we'll talk about power and sample size, which will save you months on doomed projects. So by the end of today, you'll be able to look at any orthopedic study and understand not just what they found, but how confident we should be in those findings. You'll know why some negative studies might actually be showing real differences and why some positive studies might be BS. This is the stuff that separates students who just memorize from those who really understand research. Ready? Let's make you statistically dangerous. So the first part of this is going to be on the logic of hypothesis testing. And I'm going to explain this the way I wish someone had explained it to me as a med student. So think of hypothesis testing as a criminal trial. In court, we start with the assumption that the defendant is innocent. That's not because we believe they're innocent. It's just our starting point. We then look at evidence and decide if there's enough to reject that assumption of innocence. Statistics works the same way. We start with the null hypothesis, and usually there's no difference between treatments, or that's the hypothesis at least. Not because we believe there's no difference, but because that's our starting point. We then look at our data, which is the criminal evidence, and decide if there's enough evidence to reject that assumption. And so going back to our ACL study, the null hypothesis is there's no difference in failure rates between the new and standard techniques. The alternative hypothesis is there is a difference. And our job is to see if the data provides enough evidence to reject the null hypothesis. Now, here's where it gets interesting. Just like in court, we can make two types of errors. Type 1 error is convicting an innocent person. In statistics, that's like saying there's a difference when there really isn't. That's a false positive. And you publish that your new technique is better, and surgeons start using it, but it's actually no better. That's bad. Then type 2 error is letting a guilty person go free. In statistics, it's like saying there's a difference when there really isn't. This is a false positive, and you publish that your new technique is better, is letting a guilty person go free. But we set our bar with this significance level, usually 0.05. So that means we'll accept a 5% chance of a type 1 error. And why 5%? It's arbitrary. This guy, Ronald Fisher, suggested in the 1920s, and it stuck. Now, some fields use 0.01, some use 0.1. Orthopedics generally sticks with 0.05. And then we can talk about p-values as well, because everyone misunderstands these. A p-value is not the probability that your hypothesis is true. So it's not the probability that your treatment works. The p-value is the probability of seeing your data, or more extreme data, if the null hypothesis were true. It's asking if there really was no difference between the techniques for ACL, how likely would we be to see a difference if this big only by chance? And so I'll use a concrete example here. You flip a coin 10 times and you get like 8 heads. Is the coin biased? The null hypothesis is a fair coin. So the p-value asks, if this really were a fair coin, what's the probability of getting 8 or more heads out of 10 flips? The probability is about 0.055. And since that's greater than 0.05, we don't reject the null. We can't conclude the coin is biased. But what if you flipped 100 times and got 80 heads? Now the p-value is super, super tiny, less than 0.0001. You know, getting 80 heads out of 100 with a fair coin is basically impossible, very difficult. So we reject the null and conclude that the coin is likely to be biased. The same logic goes with an ACL study. We saw 5% failure versus 8%. The p-value of 0.08 means if there really was no difference between techniques, there's an 8% chance we'd see a difference this big or bigger by random chance. Since 8% is more than our 5% cutoff, we can't reject the null. But here's what drives me crazy. People interpret this as there is no difference. Wrong. We just didn't have enough evidence to prove a difference. It's like a jury saying not guilty. That doesn't mean innocent. That just means there's not enough evidence to convict. So this brings us to statistical versus clinical significance, which is huge in orthopedics. Statistical significance just means it's unlikely due to chance, but clinical significance means it matters to patients. You might show that a new implant increases range of motion by maybe 2 degrees with a p-value of 0.0001. Super statistically significant. But does any patient care about 2 degrees? Probably not. Conversely, in our ACL study, reducing failure from 8% to 5% would be clinically meaningful. That's preventing 3 failures per 100 patients. But we couldn't prove it statistically here. This is why we need to think beyond just p-values. So then effect size is another issue, and that's telling you how big the difference is. So in our ACL example, the absolute risk reduction would be like 3%, and the relative risk reduction will be 37.5%. That's a meaningful effect size. The problem wasn't that our treatment didn't work, it's that we didn't have enough patients to prove it. Let me give you another example that shows why this matters. Study A compares 2 hip fractures, or 2 hip approaches in 10,000 patients, and they find the anterior approach, which has a dislocation rate of 0.8% versus 0.9% for posterior, p equals 0.03. So that's super statistically significant, right? Study B compares the same approaches in 200 patients. Anterior has 1% dislocation, 3% posterior, p is 0.08, not significant. So which study is more convincing that anterior is better? Study B shows a much bigger effect, but they couldn't prove it statistically due to a small sample size. Study A showed a tiny difference that probably doesn't matter. And that's why you can't just look at p-values. So now I want to move on to confidence intervals here, which honestly give you way more information than p-values. So a confidence interval gives you a range of plausible values for the true effect. The key word's plausible, though. A 95% confidence interval means that if we repeated this study 100 times, about 95 of those intervals would contain the true value. Let me make this more concrete. So say we measure the success rate of a new shoulder arthroscopy technique in 50 patients. We find 40 successful outcomes. That's 80%. But that's just our sample. What's the true success rate in the population? So the 95% confidence interval might be 67% to 89%. That means we're 95% confident the true success rate is somewhere in that range. Could be 67%, could be 89%, could be anywhere in between. But probably not 50%, probably not 95%. Here's why CIs are better than p-values. A p-value just tells you significant or not, yes or no. A confidence interval tells you the range of plausible effects, much more useful. So let's go back to our ACL example here. We found 5% failure for new technique versus 8% for standard. Difference 3%, but what's the confidence interval for that difference? Maybe it's negative 1% to 7%. This tells us so much more than p equals 0.08. The negative lower bound means that new technique might actually be 1% worse, but it could also be 7% better. Most of the interval suggests benefit, but we can't rule out slight harm. That's way, way more nuanced than not significant. So how to interpret CIs in practice then, if you're looking at a difference between treatments? If the CI doesn't include 0, the difference is statistically significant. If the CI includes 0, it's not statistically significant. The width tells you the precision, narrow is precise, wide is imprecise, and the location tells you the likely effect size. Then for ratios like relative risk or odds ratios, the null value is 1, not 0. So a CI of 0.8 to 1.2 includes 1, meaning not significant. So I'll show you how this works in real papers. A study reports the new plate reduced non-union rates with a relative risk of 0.6. So that's 95% confidence interval from 0.4 to 0.9. What does that tell us? Well, the relative risk is 0.6, meaning 40% reduction in non-unions. The CI goes from 0.4 to 0.9, which doesn't include 1, so it's statistically significant. At worst, it's a 10% reduction, relative risk of 0.9. And at best, it's a 60% reduction, relative risk of 0.4. So even the worst case scenarios shows benefit. Compare that to, relative risk 0.6, 95% confidence interval, 0.3 to 1.2, same point estimate, but now the CI includes 1, not statistically significant. The treatment might reduce non-unions by 70% with a relative risk of 0.3, or increase them by 20% with a relative risk of 1.2. But that's too much uncertainty to draw conclusions. So a practical tip then for reading papers is always look at confidence intervals, not just p-values. The CI tells you both the statistical significance and the range of plausible effects. P-values only tell you the first part. And here's something that blows students' minds. You can have a statistically significant result that includes clinically unimportant effects. Say a new rehab protocol increases knee flexion with a mean difference of 5 degrees. So that would be, maybe 95% confidence interval, 1 to 9 degrees. It's statistically significant because the CI doesn't include 0. But even in the best case scenario, 9 degrees, it might not matter to patients. This is why in ortho, they're moving toward reporting minimal clinically important differences, or MCIDs. So for knee flexion after TKA, the MCID might be 10 to 15 degrees. So our statistically significant 5-degree improvement does not reach clinical significance. So on to kind of the third component of this lecture, which would be selecting the right test. And this is going to be the part that saves you in research meetings, choosing the right statistical test. And I'm going to give you a decision tree that works in about 90% of times. The first question you always want to ask is, what type of outcome variable do I have? Continuous, ordinal, or categorical? So that really determines everything. Continuous outcomes, that's range of motion, surgical time, blood loss. But if you're comparing two groups with continuous outcomes, your first thought should be t-test. But hold up, t-tests have assumptions, right? The data should be roughly normally distributed. How do you know? Look at a histogram. If it's bell-shaped, you're good. If it's skewed, you got problems. So a real example is surgical times are often skewed. Most cases take 60 to 90 minutes, but a few disasters take 3+ hours. That long tail screws up the t-test. So what do? You got two options here. Option 1, you transform the data. You take the logarithm of the surgical times, which often makes them normal, and then you do your t-test on the log transformed data. But this makes interpretation really hard, especially if you're sending it to another colleague if they want to write the results. And then, they're another medical student and they're not as, they're not trained in log transformed data. Option 2, use a non-parametric test. So the Mann-Whitney U test is really your friend here. And it compares medians instead of means and doesn't care about normality. So the downside is it's less powerful, meaning you need more patients to make a difference. But wait, what if your groups are paired? So measuring range of motion before and after surgery in the same patients. Now you need paired tests, and paired t-tests for normal data will Coxicon signed rank for non-normal. The pairing is really important though. So, I once saw someone analyze pre-op and post-op pain scores with an unpaired t-test, and, they got roasted because by ignoring the pairing, he threw away tons of statistical power. So now what if you're comparing more than two groups? Say you're looking at pain scores with 3 different post-op pain protocols. So for our normal continuous data, you use ANOVA, analysis of various, but ANOVA just tells you there's a difference somewhere. It doesn't tell you which group or which groups differ. So you need post-hoc tests like Turley's or Tukey's, I believe, to figure out if protocol A beats protocol B, B beats C, or whatever. So for non-normal data with multiple groups, you use Kruskal-Wallis, and same deal, it tells you there's a difference somewhere, then you need post-hoc tests. But this is a critical point about multiple comparisons. If you compare 3 groups, you're actually making 3 different comparisons. You're doing A versus B, B versus C, and A versus C. So each comparison has a 5% chance of false positive. Do enough comparisons and you'll find something significant by chance. That's why we do corrections like Bonferroni. So you divide your significance levels by the number of comparisons. Then we want to move on to categorical outcomes, and that's things like complication yes, no, fusion achieved, not achieved, etc. So for comparing those 2 groups with categorical outcomes, you want chi-square test. That's your go-to. Classic example, comparing infection rates between 2 surgical approaches. So you make a 2x2 table, approach anterior, posterior, by infection, yes or no. Chi-squared tells you if infection rates differ. But chi-square has a dirty secret. It keeps decent sample sizes. So the rule of thumb is every cell in your table should have at least 5 expected counts. And what if you're studying a rare complication that happens in only 2 patients? Chi-square breaks down. That's where you use Fisher's exact tests, and it works for any sample size, but gets computationally intensive for big samples. Most software automatically switches to Fisher's when samples are small. And then for paired categorical data, like asking if patients improved yes or no at different time points, you use McNemar's test. And almost no one knows about this one, but it comes up in orthopedics all the time. And, you know, this podcast is getting a little long right now, and I want to respect your time as well as mine. So let's pause here, and I will get to the 3rd lecture where we'll continue about correlation and regression, because that's where things get powerful. Thank you very much, and I will see you again on lecture 3.